So good morning. In this lecture, we discuss about the sum of the properties of the closeness, boundedness, and compactness in a finite dimensional nonlinear space. So compactness in metric space is said to be compact if every sequence in X has a convergent subsequence, and a subset M of X is said to be compact if M is compact considered as a subspace of X, that is, for every sequence in M has a convergent subsequence whose limit is an element of M. A compact subset M of a metric space is closed and bounded. So first we have to prove that the M is closed, that is M is equal to B M bar. So as we know that the M is a subset of M bar, so it is enough to show that the M bar is a subset of a M. So let X belongs to be M bar. So there exists a X sequence Xn in M such that Xn converges to be X under the metric D. And since M is compact, so every subsequence has a convergent subsequence. That is X and K converges to be X, belongs to be M. So therefore, the closure of M is a subset of M, and hence M closure is equal to be M, that is M is closed. So now we have to show that M is bounded. So suppose that M is not bounded. So there exists a sequence yn in M such that distance between yn and y is greater than n for some y in M. So therefore the sequence yn cannot have a convergent subsequence, which contradicts the fact that M is a compact, and hence our supposition is wrong. It means that M is bounded. So we get the result. But the converse of this result is not true in general. For example, say that we consider the sequence En in a space L infinity with the norm x infinity is equal to supremum of xi, where En is equal to be delta nj, has the nth term as a 1 and all the other terms are 0. That is, E1 is equal to be 1, 0, 0, and so on. E2 having a 1 in the second place, E3 having a 1 in the third place. So this sequence is bounded and norm of En is equal to be 1. Its term constitute a point set which is closed, but it has no point of accumulation. So, but the sequence En has a no convergent subsequence. The point set is not compact. So now let's discuss next part. In the finite dimensional space X, any subset M subset of Ax is compact if and if only M is closed and bounded. So we have now discussing about in our metric space. Now we can say that this result, whatever we have discussed, so in finite dimensional space that result is true. So in a finite dimensional nonlinear space, any subset M is compact if and only if M is closed and bounded. So the previous the result we have already said the compactness implies the closeness and boundedness. So now suppose that the M is closed and bounded. Now we have to check it out whether it is compact or not. So we have to check it out with the compactness. Now suppose that the dimension of X is equal to be n, and E1, E2, so on, En is the basis for the X. And we can consider any sequence xn in a M such that the xm is equal to be xi1 m e1 and so on xn m en. Now since M is bounded, so we can say that the norm of xm is less than or equal to be k for all M. And by using up the property in a finite dimension, we have already discussed up that. So this k is greater than or equal to be norm of a xm, and this xm can be uniquely written as a these summation of xi ei's over the i's 1 to n, which is greater than or equal to be a c into summation of a modulus of these scalars xi j m, where c is greater than 0. So hence the sequence of the numbers xi j m, where j is a fixed, is bounded, and by using the Bolzano's Weierstrass theorem, it has the point of accumulation says ii. So we can conclude that the sequence xm has a subsequence says em, which converges to be this g, and since m is closed and z belongs to em, So this shows that there is an arbitrary sequence xm in M which has a subsequence which converges in M, and hence M is a compact. So our discussions here show that in a finite dimensional space, the compact subsets are precisely closed and bounded subsets. So this property can be used for the defining compactness in a finite dimension. However, this can no longer be done in a class of a infinite dimensional nonlinear space. So using a Paris lemma, we can extend up that part. So let y and z be subspaces of a norm space of any dimension, and suppose that y is a closed and proper subset of a z. Then for every real number theta in the interval 0, 1, there is a z belongs to be a z, such the norm of a z is equal to be 1 and norm of a z minus y is greater than or equal to be theta. So we consider any v belongs to be z minus y and denote its distance from y by a. That is, a is equal to be infimum of a norm of a y minus a. So here see that this is being this distance is a. We have found up here, and clearly this a is greater than 0. And since we have this y is closed, so we can take any theta in the interval 0, 1. So by the definition of an infimum, there is a y naught in a y such that a is less than equal to b norm of a v minus y naught, which is less than equal to b a by theta. So a by theta is greater than a. Since theta lies between 0 and 1, so let we have a z which is equal to be c into the v minus the y naught, where c is equal to be 1 by norm of v minus y naught. So then this norm of a z, if you consider, which is equal to be norm of the v minus v naught over the norm of a c, where norm of a c is equal to be again 1 by norm of v minus y naught. So we get the norm of a g is equal to be 1. So which shows that the norm of a z minus the y is greater than or equal to be theta for every y in a set y. So we have the norm of a z minus y, which is equal to be the norm of a c into the v minus y naught minus y. So we can common up as this c by using a definition of norm. This is equal to be a modulus of a c, and we know that the modulus of a c, because c is positive, is equal to c into the v minus the y naught minus the c inverse y. And suppose that this is the y1. So this is equal to be the c times the norm of a v minus the y1. So this form of a y1 shows that the y1 belongs to be y. The hence norm of a v minus y1 is greater than or equal to be a by the definition of a. So we can divide up to c, and using up we can say that the norm of a z minus the y is equal to be a c times the norm of a v minus y1, which is greater than or equal to be c into the a, and c is equal to be 1 by norm of a v minus y naught, which is greater than or equal to be a by theta, so which is equal to be theta. So hence the result. So here we have get the result. So in a finite dimensional nonlinear space, the closed unit ball is compact. Conversely, the Rees lemma gives the following useful and remarkable result. So if a norm space X has a property that the closed unit ball M is compact, then X is a finite dimension. So we assume that M is a compact, but the dimension of X is, say, infinity. Now, and show that this leads to a contradiction. So we choose any x1 of the norm 1, that is the norm of x1 is equal to be 1. And this x1 generates a one-dimensional subspace a x1 of the x, which is the collection of a alpha x1, which is closed and proper subspace of ax. So by the Rees lemma, there is an x2 in ax of the norm 1 such that norm of x2 minus x1 is greater than or equal to be theta, and suppose that theta is equal to be 1 by 2. And in particular, again, norm of x3 minus norm of x1 is greater than or equal to be 1 by 2, and so on. Proceeding, we obtain a sequence of xn of the elements xn belongs to be m such that the norm of xm minus xn is greater than equal to be 1 by 2. So this tells us that the sequence xn cannot have a convergent subsequence, and this contradicts the compactness of am. So our assumption that the dimension of a x is infinity is false. So it is a finite dimensional space. Thank you.